All right. So now we're getting into the idea that light is energy and light's a particle. So light is a particle because it's going to knock electrons free with a certain amount of energy because we can measure the kinetic energy of those electrons as they get knocked free from metallic surfaces. Now, this is how solar panels work. So let's jump into it. This is the photoelectric effect. And again, this is what Einstein won his Nobel Prize for. So, 11 series of measurements were taken. The kinetic energy of the electrons were emitted from metallic, and then they were measured. So we have a table below. We have the light frequency, so 5 times 10 to the 14th, 6 times 10 to the 14th, 7. So these are very high frequencies. I mean, this looks like 5 to the 14th. I don't know what that is, what type of light that is, but whatever. I feel like that's like green through ultraviolet there. But I don't remember the numbers. Anyway, maximum kinetic energy of the electron. So it looks like 5 is giving us an electron there. So we'd come over to 5 here, frequency of 5 times 10 to the 14th, and we'd go up to 0.1. So, oh look, they're already 0.1. So I just put a dot right there. Boom. There's my 0.1. All right, so then I go to the next one, 6 and 0.45. So, of course, that's like halfway in between there, right? Right there. 7 is 0.95, so almost a 0.1, but not quite, so 0.95. 8 times 10 to the 14th is 1.3, so we'll go to 1.5, drop down 2, right about there. And then we see a light has 9 times 10 to the 14th, and we get 1.45. So we're going almost to there. All right, so notice they're not a perfectly straight line. That's okay. We can still draw a line of best fit. So we plotted them, check. Now we're going to draw the line to get us an estimate of it. So we're gonna kind of sketch it, and I'm gonna try and hit it at one shot. You can do this. I mean, I guess this is a fine way of it. If you have a ruler, that'd be the best way. I'm just gonna kind of sketch that straight line right down there. Yeah, close enough. Probably should have tried to draw it straighter, but whatever. So there it is. And I got my graph. That's it. A done. That's 3 points. Just plot and make a graph. All right, determine the cutoff frequency. Remember, cutoff frequency is the frequency below which no electrons are released. So we'll just look right there. Actually, here, let's do that in color so that it relates. So there's that. And so the cutoff frequency is just read from the graph of 4.5 times 10 to the 14th hertz. I just read it right from the graph. All right. Determine the work function of the metal. So the work function is the energy associated with the cutoff frequency. Energy of cutoff. So our energy of a wave is just equal to h times f. I'm using this equation, energy is h times f, because I know the frequency. That's right. So our Planck's constant here is 4.14 times 10 to the negative 15th, all right? And then that's going to be times our frequency, 4.5 times 10 to the 14th, and that's going to give me an energy of 1.86 electron volts. It should be EV, little EV. EV. All right, and so that is the work function. That's the energy of the thing. So that equals W for this particular metal. So all the electrons are going to need 1.86 electron volts of energy to get free from the metal. All right, photon with a frequency of 3 times 10 to the 14th hertz strikes the surface. Well, we don't have to convert this to energy because we know the cutoff frequency. Let's see, cutoff. We'll just write cutoff. Cutoff is equal to 4.5 times 10 to the 14th, and we know that is greater than 3 times 10 to the 14th. So no electron. That is a smaller frequency, and so it is less energy. We need more than 4.5 to get there. Now, the next one, we see that 4.5 times 10 to the 14th is less than this 10 times 10 to the 14th. So yes, we get an electron. Yes, we get an electron there. All right, if yes, calculate the kinetic energy of the electron. So we need to figure out how much energy that electron's got. So if we jump all the way to the equation we're going to use, kinetic energy of the electron is equal to the energy of the photon minus the work function. So we need to calculate some things. I already know the work function, but I need to get the energy of the photon. So the energy of the photon is going to be h times f again. In this case, it's going to be 4.14 times 10 to the negative 15th. Now it's times 10 to the negative 14th. And that gives me an energy of the photon of what, 4.14? 4.14 electron volts. All right, so that's my energy. Put some red here. That's my energy of my photon. So that's going to go right in there. My work function was from above. Green, right? Green, green, green. And so I can find the kinetic energy of that. All right, so we'll say 4.14 minus the 1.86. And again, let's talk about this real quick. Use my computer here. Energy of the photon, 4.14 electron volts. That's how much energy it's got. It's going to take 1.86 of that to get out of the well, but then everything else is going to be left over as the kinetic energy. So all we're doing is finding what's left over after we bump it out of the energy well of the work function. And so that's going to equal 2.28 electron volts. That's it. All right, finally, light for a given frequency falls on a metal surface, causing electrons to be ejected from the metallic surface with some kinetic energy. What would happen if the frequency of light were doubled? If you double the kinetic energy, your initial thought would be like, oh, well, it's going to, or excuse me, you double the light energy frequency, you double the light energy, well, therefore you double the kinetic energy. But that's not true. It won't fully double. It'll actually be even more than that. So let's see what we got. One photon with the same kinetic energy would still be emitted. I think an electron's being emitted, so that's not right. One photon would be emitted, but with greater kinetic energy. I think those are supposed to say electrons. I think this was the correct. This should have said electron. This should have said electron. And this should have said electron. That would make more sense. Let's try this again. One electron with the same kinetic energy. Well, that's not right. All right. One electron would be emitted, but with greater kinetic energy. That's sounding pretty good so far. That's sounding pretty good. Multiple electrons with the same kinetic energy. No. This is a really big one. One photon can only cause one electron there. That's the whole idea of this particle nature of light, is that one particle interacts with one particle. So the photon interacts with one electron. So that's not true. C is definitely not true. And then no electron. Well, no, if it's a higher energy photon, it's still going to emit that electron. So sure enough, B is our best choice there. All right. That is, we don't know page numbers anymore. So that is questions 11 and 12. All right.